Welcome to our third lecture on Cstar algebras titled States and the Gelfand-Naimark-Segal Theorem. This is part 1 of our lecture titled Positive Elements in a Cstar algebra. The goal here is to start from a Cstar algebra and construct Hilbert spaces on which this Cstar algebra act. To do so, I want to study certain sesquilinear form on Cstar algebras defined using linear functionals of a Cstar algebra and the adjoint operation. So concretely, let's fix some Cstar algebra and let phi be some continuous linear functional on that Cstar algebra. For any two elements a and b in the Cstar algebra, I define the pairing of a and b as the scalar phi of a star b. It's easy to check that indeed this pairing is sesquilinear, that is, it is conjugate linear in the first variable and linear in the second variable. Moreover, because I've assumed that phi is a continuous linear functional, using the fact the adjoint is an isometry and the norm of a Cstar algebra is submultiplicative, I get that this sesquilinear form is continuous on the Cstar algebra. But what is interesting to me is when is this construction giving me a pre-inner product? So what I mean is that I would like that in particular the pairing of a with itself is some non-negative number, and that there is some symmetry, namely that this sesquilinear form is also Hermitian. Clearly, it's a bit too demanding to ask for this pairing to be an actual inner product, that is, to ask for a pair with a to be 0 if and only if a is 0, because we apply some arbitrary linear functional. We expect this has a large kernel. It's not completely clear how this is going to play, and we'll study that later. But at a bare minimum, I would like this pre-inner product and then hope that I can always quotient by the right subspace to get my Hilbert space later on. So I'm going to focus first on the positivity condition, this first of the two conditions here. So certainly if I get a positive sesquilinear form out of a particular choice of a linear functional phi through this construction, then by replacing phi with minus phi, I'd get a negative sesquilinear form. So in other words, I can't expect positivity to hold for any possible continuous linear functional on my Cstar algebra. So a natural definition arises. A linear functional of a Cstar algebra is positive when for any element a of your Cstar algebra, the functional evaluated at a star a is indeed positive. Now, it's important to note that I do not require actually the functional to be continuous at this moment. So positive linear functional is really a linear map in the algebraic sense from the Cstar algebra to the complex numbers with this extra positivity condition. And we will see later on that in fact, positive linear functionals are automatically continuous. Among those, there are the states. The states are positive linear functionals of norm actually 1, as element of the dual of your Cstar algebra. And later on, we will actually focus most of our attention on states among all the positive linear functionals, because indeed, if a positive linear functional is continuous, then up to normalizing it, it becomes a state. Now, the question that you could ask is, what is special about the elements of the form a star a for a, an element of a Cstar algebra? And we are going to spend this first part of the lecture studying those elements in quite some detail. So first I'm going to give a name to these elements and I'm going to call them positive, which is maybe natural in sight of the definition for positive linear functional. But we're going to justify this terminology in hindsight by actually showing that an element of a Cstar algebra is positive exactly when its spectra is contained in the positive half-line and it is self-adjoint. So this is, of course, a very important result in this theory of Cstar algebra, and it requires more sophistication than you might at first guess, because our Cstar algebras here are abstract objects. They're not yet acting on Hilbert spaces. In fact, it is the purpose of these lectures to get to show that Cstar algebras are really up to a star isomorphisms, some algebras of bounded operators on some Hilbert space. So at the moment, we need to go from this abstract notion of positivity that may seem a little bit artificial, though I hope I introduced it in a way that makes some sense, to actually connecting it with a much more natural spectral notion of positivity. To do so, I'm going to go through several steps. The first thing I'm going to do is look at when do I get self-adjoint element whose spectrum lives in the positive half-line. And one way to do that is to pick an arbitrary self-adjoint element of your Cstar algebra and squaring it. So let's pick a self-adjoint element A in some unital C-star algebra, and let's denote by B the unital C-star algebra generated by this A and the unit of your original C-star algebra. Now, because A is self-adjoint and of course commute with the unit, it's easy to check that B is an abelian C-star algebra. It is the closure of the set of all the linear combinations of powers of A and A star, which all commute with each other, and of course the unit. So, as an abelian unital C-star algebra, it's star isomorphic to the continuous function on some space, and here, of course, the space is going to be the spectrum of A. So B is star isomorphic to the continuous function on the spectrum of A, and it is in fact so via the Gelfand transform. Now, a result we've studied when we studied the Gelfand-Naimark theorem is that the spectrum of A square is also the spectrum of the Gelfand transform of A squared. In other words, the range of the square of the Gelfand transform of A. And, well, we already knew that our element A was self-adjoint, so its spectrum was a subset of the real line. So when you square that, you get a subset of the positive half-line. In other words, the spectrum of A square is indeed a subset of the positive half-line as stated in the theorem. Alright, so at least we have a good source of elements that have a so-called positive spectrum. Now, in order to relate elements in a C-star algebra of the form x star x, that is, positive elements, with self-adjoint elements whose spectrum is a subset of the positive half-line, I need a core lemma that I'm now going to prove, which characterizes those self-adjoint elements with positive spectrum. So let A be a self-adjoint element in some unital C-star algebra. The following assertions are equivalent. First, the spectrum of A is a subset of the positive half-line. Second, for all t greater or equal than the norm of A, we have that the norm of t minus A is less or equal than t. And third, there exists a t greater or equal than the norm of A, such that the norm of t minus A is less or equal than t. Let's prove our theorem. Let's start with assumption 1. So we have A, a self-adjoint element, such that the spectrum of A is a subset of the positive half-line. And now we pick t greater or equal than the norm of A. I'm going to work with the Gelfand transform again, which is a star isomorphism from the C-star algebra generated by A and the unit onto the C-star algebra of the continuous functions on the spectrum of A, since A is self-adjoint. As a star isomorphism, the Gelfand transform is an isometry, so the norm of A equals to the norm of the Gelfand transform of A. Okay, so let's see what we can deduce from this. Let's pick Z, a point in the spectrum of A. By assumption 1, Z is positive, so we have t minus Z is less or equal than t. But on the other hand, t was chosen greater or equal than the norm of A, which is equal to the norm of the Gelfand transform of A, and that's a supremum norm. So it is the supremum of the modulus of all the values in the range of the Gelfand transform of A, which here is, of course, equal to the spectrum of A. All right. So that means that since Z in the spectrum of A, in other words, that's an arbitrary point in the range of the Gelfand transform of A, then by assumption, t is greater or equal than Z. In other words, t minus Z is positive. So putting all that together, what we have is that if we calculate the norm of t minus A, that equals to the norm of the Gelfand transform of t minus A, since the Gelfand transform is an isometry. We know how to calculate the norm of a function on the spectrum of A. It's a supremum norm. And you see in our supremum norm that the modulus of t minus z can be dropped to simply t minus z because t minus z is positive. We also see that t minus z is less or equal than t for all z in the spectrum of A, so we get the desired inequality. Of course, assertion 2 implies assertion 3. That's straightforward. So now I'm going to assume 3 and try to prove 1. Now, again, I have an element A, self-adjoint, and a real number t, so that t is greater or equals than the norm of A, and at the same time, the norm of t minus A is less or equals than t, and I would like to prove that the spectrum of this A is contained in the positive half-line. So, just as before, I'm going to work with the Gelfand transform on the C-star algebra generated by A and the unit. And my assumption here that as the norm of t minus a is less or equals than t translate, again using the isometric property of the Gelfand transform, to the norm of the Gelfand transform of t minus a is less or equals than t. And remember, again, the norm of the Gelfand transform is a supremum norm. So what we get is that t is greater or equal than the modulus of all the values in the spectrum of t minus the Gelfand transform of a, or in other words, if z is the spectrum of a, we have that t minus the Gelfand transform of a at z, which is actually z, is less or equal than t. Okay? So remember that the Gelfand transform of a of diluted at z is actually z. It's the same thing. The Gelfand transform of a in this case acts as the identity, of course. So in particular, what we've seen is that the Gelfand transform of a applied at an arbitrary element in the spectrum of a is a non-negative number. And therefore, the spectrum of a, which is equal to the spectrum of the Gelfand transform of a, which is the range of the Gelfand transform of a, is indeed contained in the positive half line, and assertion 1 holds. So now I can extract an important corollary from my previous theorem. If A and B are two self-adjoint elements of some unital C-star algebras, both of which have spectra contained in the positive half line, then their sum has spectrum contained in the positive half line. Note that the sum of two self-adjoint elements is always self-adjoint. So here we're saying that adding self-adjoint element with positive spectra gives you self-adjoint elements of positive spectra. So let's prove our theorem. So since A is a self-adjoint element with positive spectrum, the previous theorem tells me that there exists t sub A greater or equal than the norm of A, such that the norm of t sub A minus A is less or equal than t sub A. In fact, the previous theorem tells me I could choose t sub A equals the norm of A if you want. And then, again, because B is self-adjoint and has positive spectrum, there exists a real number t sub B greater or equal than the norm of B, such that t sub B minus B in norm is less or equal than t sub B. Okay, now let's do a couple of simple calculations. So first, note that by the triangle inequality, the norm of A plus B is less or equal than the norm of A plus the norm of B. And by assumption on our t's, that's less or equal than t sub A plus t sub B. So for getting the middle part, we have that the norm of A plus B is less or equal than t sub A plus t sub B. But on the other hand, if you look at the norm of the sum t sub A plus t sub B minus the sum A plus B, then by rearranging your term in an obvious manner and using the triangle inequality, this in turn is less or equal than t sub A plus t sub B again. So if you look at this, you observe that A plus B is also self-adjoint. It's an easy calculation, and you conclude that we can apply our previous theorem once more and indeed conclude that the spectrum of the sum A plus B is a subset of the positive half-line. So if you add two self-adjoint elements with positive spectrum, you get a self-adjoint element with positive spectrum, and they need not commute for this to be true. So what we've shown actually is in particular that if you fix some unital C-star algebra and you define C as a set of those self-adjoint elements in your C-star algebra whose spectrum is contained in the positive half-line, then C is a cone in the real vector space of self-adjoint elements of your C-star algebra. So being a cone means you're closed under addition, and we just proved that, and you close under scalar multiplication by a positive scalar, which is trivial to check. What's interesting about this is that if your cone has certain properties, then you can use it to define an order. So here, what I mean is, suppose you have an element A in your cone, so that minus A is also in your cone. Then the spectrum of that A must be both positive and negative, so it's actually reduced to the singleton 0. And since A is self-adjoint, you can use a Gelfand transform to conclude A must be 0. In addition, if you take any self-adjoint element using the Gelfand transform again, and we'll see that again in a couple of slides, then we will see that we can write A as a difference of two elements of my cone. Put together, this means that I can define an order on the vector space of self-adjoint elements. If A and B are two self-adjoint elements, then I can say A is less or equal than B, if and only if B is minus A is in the cone, which is equivalent to asking the spectrum of B minus A to be in subset of the positive half-line. So if you do that, actually the self-adjoint element with this order becomes what's called an order unit space, which is a special kind of ordered vector space, and the order unit is the unit of your C-star algebra. However, this order is extremely badly behaved with respect to the multiplication. In fact, if you multiply two self-adjoint elements in general, you do not expect to get a self-adjoint element because the adjoint operation is anti-multiplicative, and it's easy to find counterexamples of that even with 2x2 matrices. So this is well-defined. This is a well-defined order, well-behaved order. So this is a well-behaved order with respect to the linear structure, but it is extremely badly behaved with respect to the multiplicative structure. Nonetheless, now we have to address an ambiguity. We have an order on the set of self-adjoint elements, and so it makes sense to ask for an element to be positive by simply saying it's greater or equals than 0. But at the same time, we already defined the notion of positivity in Cstar algebras. We need to resolve this ambiguity. So now I'm ready to prove the fact that in a Cstar algebra, positivity in the sense of being of the form x star x is equivalent to positivity in the sense of being self-adjoint with a positive spectrum. And to do that, I start with a lemma, which says that if x is an element of a unital Cstar algebra, such that the spectrum of x star x is a subset of the negative half-line, then actually x must be 0. I'm going to prove this result, but I want to insist first and foremost that x and x star are not assumed to commute. X is not normal, because that is actually what makes this proof difficult. So first, note that I would like to know something about the spectrum of x star. And the spectrum of x star does not equal the spectrum of x star x in general, but in any unital Banach algebra, what is true is that the spectrum of x star without 0 equals to the spectrum of x star x without 0. And from this, you can easily conclude the spectrum of x star is indeed also a subset of the negative half-line. So we can conclude that x star x plus x star is the opposite of the sum of two self-adjoint elements with positive spectra, and so itself must have negative spectrum. Now I'll make another observation. I'm going to write x as its real part plus I times its imaginary part, where the real part of x is x plus x star over 2, and the imaginary part of x is x minus x star over 2i. Then if I compute x star x plus x star, I get twice the sum of the square of the real part of x and the square of the imaginary part of x. Let's pause for a moment, because this is where having x and x star not commute is important. If x and x star did commute, then x star x would already be equal to the square of the real part of x plus the square of the imaginary part of x. The cross terms would already simplify, and then of course I could conclude that x star x is positive in the sense of self-adjoint elements, and that'd be done. But since here x and x star do not commute, I must do this calculation here of x star x plus x star to see the cross term cancel. What I can conclude from this computation is that since the square of the self-adjoint element real part of x is itself self-adjoint with positive spectrum, and similarly the square of the imaginary part of x is a self-adjoint element with positive spectrum, their sum is again a self-adjoint element with positive spectrum, and twice that still is a self-adjoint element with positive spectrum. So putting all that together, I've shown that the spectrum of x star x plus x star is indeed a subset of the positive half-line. This is an important observation, because now I can conclude that the spectrum of x star x plus x star is in fact the singleton 0. It has to be contained at once in the positive and the negative half-line. What I can deduce from this is that since x star x plus x star is self-adjoint, it must be 0. Again, the trick, if you want, is applies the Gelfand transform to the Cstar algebra generated by the unit and the element x star x plus x star. Since the spectrum is reduced to singleton 0, you'll see immediately that we must have this identity. But what does it mean for x star x plus x star to be 0? Well, it means that the real part, the square of the real part of x is equal to the opposite of the square of the imaginary part of x, because you solve in the displayed equation above equals 0. And what does that tell me? Well, I know that the spectrum of the square of the real part of x must be a subset of the positive half-line, because it's a square of a self-adjoint element. I know the same thing about the square of the imaginary part of x, therefore, minus the square of the imaginary part of x must have negative spectrum. And so again, the spectrum of the square of the real part of x ends up having to be the singleton 0. And again, because the real part of x is a self-adjoint element, this forces the real part of x to be 0. Once I know that, I can solve any way you want to conclude that the imaginary part of x is 0. There are different ways you can get it. And if the real part and the imaginary part of x are both 0, then x is 0. And I've concluded my lemma. So this is very nice. And we're going to use this as a core of the argument of the main theorem, which is this theorem. So this theorem tells us that we can now resolve sort of the slight apparent ambiguity between positivity in the sense you have the form x star x and positivity in the sense you're self-adjoint with positive spectrum. They are the same. So if you start from some unit or C-star algebra and you pick an element A in your C-star algebra, the following conditions are equivalent. The first is A is positive in the way we started this lecture. It's of the form x star x. The second is A is self-adjoint and its spectrum is a subset of the positive half-line. And the third is that in fact A is the square of some self-adjoint element. So let's prove this important result. The difficult part is to prove that 1 implies 2. So let A be given such that A equals x star x for some x in your C-star algebra. Again, the Gelfand transform is a star isomorphism from the C-star algebra generated by A onto the C-star algebra of continuous function on the spectrum of A, since A is self-adjoint. And we can use that to define two new elements that I'm going to call A plus and A minus. So what A plus is the unique element in the C-star algebra generated by A in the unit, such that the Gelfand transform of A plus is a function square root of the positive part. That is square root of the max between the variable and 0. Similarly, A minus is a unique element of the same C-star algebra whose Gelfand transform is the square root of the max of negative the variable 0. These two functions, the square root of the positive part and the square root of the negative part, are of course continuous functions on R, and the spectrum of A is a subset of R since A is self-adjoint. So this is well defined. These are elements of the continuous function on the spectrum, and the Gelfand transform is surjective, so there must be elements that maps to those two functions from the C-star algebra generated by A, and because the Gelfand transform is injective, these elements are unique. Moreover, again, using the fact the Gelfand transform is a nice star isomorphism, it's very easy to check that A plus times A minus is 0, and therefore A minus times A plus is 0 too, since the C-star algebra generated by A is abelian as A is self-adjoint. It's also easy to check, again using the Gelfand transform, that x star x is in fact the square of A plus minus the square of A minus. Basically because those results are true for the Gelfand transforms of the respective elements here inside the continuous function of this over the spectrum of A. So by the star isomorphism property, they are true as well in the original C-star algebra generated by A. Now here is a little bit of magic. I'm going to define Z as x times A minus. The reason why this is a good idea is because when I calculate Z star Z, I get something nice. I get, by definition, that it is A minus x star x A minus. Note that A minus is self-adjoint. And, well, that's minus A minus to the power 4 because A minus multiplied by A plus disappears. It's 0. So we have an expression that tells me that Z star Z is equal to minus the square of some self-adjoint element. And as such, the spectrum of Z star Z is contained in the negative half-line, since the spectrum of A minus to the 4th is contained in the positive half-line. So I know something, of course, about elements of the form Z star Z whose spectrum are contained in the negative half-line. What I know is that Z must be 0. So concluding that Z 0 here tells me what? It tells me that A minus to the power 4, which is minus Z star Z, must be 0 as well. So A minus is 0. Again, here I'm using the fact that A minus is a self-adjoint element. So I can use the Gelfand transform to check that if A minus to the 4th is 0 as an element of the continuous function on the spectrum of A, we must have that A minus as a function, as a Gelfand transform of A minus as a function on the spectrum of A must also be 0. And again, using the isomorphism property of the Gelfand transform, conclude A minus is 0. Certainly, there are elements in C-star algebra that are non-commutative. which could square or get to the power 4 to 0 while themselves not being 0. That's easy to do with 4x4 matrices, for instance. But here we have a self-adjoint element, and so the Gelfand transform guarantees that indeed I can simplify and A minus is 0. Once you know A minus is 0, you know that x star x is the square of A plus. And of course, as a square of a self-adjoint element, you have shown that x star x is indeed a self-adjoint element with positive spectrum. And that is where we have shown our main result. This is what it took to get to the conclusion that positive elements in the sense we started with are positive in the sense of the order on self-adjoint elements. So now let's prove that in fact we have an equivalence here. I'm going to prove that 2 implies 3. So I take a self-adjoint element A whose spectrum is contained in the positive half line, and I want to show that in fact it's the square of some other self-adjoint element in my C-star algebra. So what I'm going to do is I'm going to take the square root function and restrict it to the spectrum of A, which I can here, since the square root is defined on the positive half line and the spectrum is a subset of that. Let's call R the restriction of the square root. Since A is self-adjoint, we again observe that the C-star algebra generated by A and the unit is star isomorphic via the Gelfand transform to the continuous function on the spectrum of A. So there is a unique element, call it B, in the C-star algebra generated by A and the unit, such that the Gelfand transform of B is that function R, the restriction of the square root. And then it is simply an application of the Gelfand transform isomorphism properties to check that the square of that B must be equal to A. So 2 implies 3. 3 implies 1 is trivial, simply because we already, by 3, know that our element is written in the right form. So if A is B square for B being self-adjoint, well then A is B star B, because I replace one of the 2 factors of B by B star. It's the same thing, and therefore, indeed, A is positive. So we see that we have been able to fully characterize positive elements in our C-star algebras. In fact, if we put together all the characterization of positivity we've come up with during this lecture, we get this final theorem, which tells us that a self-adjoint element of a C-star algebra is positive if it satisfies one and then therefore all of these equivalent conditions. The 3 first ones are the theorem we just proved, but the 2 next ones are actually a theorem we use to characterize self-adjoint element with positive spectra, but now we know that this is the same thing as being positive in the sense we started this lecture with. So all of those statements fully describe positive elements in a C-star algebra. So equipped with this knowledge, we can move to the second part of our lecture, where we are going to return to states and linear functionals that are positive. If you recall, we want to construct certain type of pre-inner product on C-star algebras using sesquilinear forms that use linear functionals and the adjoint operations. And now we have a good understanding of the positive elements, and by proxy we'll see we can extract from that a good understanding of positive linear functionals and states, and then use them to indeed build representations of C-star algebras on Hilbert spaces.